So there's no reason to describe the workings of a voltmeter other than in this case, we're going to talk a little bit about the analog voltmeter, and so that sort of would be part of a report. Okay. So anyway, watch for an update to that document. I just Fridays mornings are also busy. I have research group meeting, and I'm getting physical therapy for my back operation, which is all good. All right. Let's see. Right. So I hope next week I hope to finish series in parallel this week. And in fact, I'm going to ask you, if we don't finish today, to look at those videos and finish the tables that we're going to look at in a little while. And then next week, we're going to look at a mixed circuit and this voltage divider circuit, or rheostat, that you see at the end of the lab manual. And it's hooked up two different ways. And it's sort of a further it's not exact. Well, it's related to the analog and digital voltmeters, but it shows you, it gives you a taste of measurement science and things that you have to think about when you make a measurement. And you may never actually use these meters again, but as pre-health people or bio majors or chemistry majors, you're going to face issues of measurement challenges. And so I think it's important that you get exposed to these situations so you keep it in the back of your mind. And when I make this measurement, am I really measuring what I think I'm measuring? That's the essence of measurement science. And another way to say it is, I want to make sure my measurement has a minimal effect on the system that I'm measuring. And today we're going to learn more about how these two meters accomplish that or don't accomplish that. The analog meter we don't use them anymore because they affect circuits too much, and people used to go through some serious gymnastics to overcome that. But nowadays we have these digital meters and we don't have to worry about it anymore. Okay, so the bottom line here, everything is sort of predicated on this Ohm's law. And I always write it as I equals V over R. It doesn't matter. There's no one single way because there's three terms, so you can make three different equations. Engineers tend to like this one, but because you think, and you'll see, because you think of voltage drops, right? We've already talked about voltage drops. And also I wanted some people did an extensive background by not exactly copying, but going through the manual. And the water pump analogy is okay. It's a bit limited. I think it's better to think about voltage. Hopefully you're going to learn in lecture. You may remember work, right? Work, energy, and there was work and energy and potential energy and kinetic energy. And you remember that's in joules, right? And so if you put a rock, if you're the coyote and you want to get the road runner, and so you roll the rock up the hill and you push it off, and somehow the mountain falls out from under you or something. But we know then the rock falls down, and we've built up this potential energy to get this kinetic energy, and it's because, and we do work to get some other work back because we want to have our dinner. So in electricity, it is the same concept, and you're going to learn about voltage is potential energy per charge, per coulomb of charge. So a battery, what a battery does, or a power supply does, is supply energy, potential energy, to the charge carriers. and then for it to do some work somewhere else. And that's the way you think about, say, the Hoover Dam. The Hoover Dam is built that uses the gravitational potential energy of the water to spin a turbine that generates electricity there, but it's a generating energy, potential energy, to be sent to your house or to factories or things to be able to do work. And so that, and you think, if you remember, voltage has to go from the power supply down to zero because now the charge carriers, they're still moving at the same rate. But as they go through the circuit, they have less and less energy to give to the next circuit element. And then most things that do work are there well, examples of things that do work, like light bulbs or a motor in your dishwasher or your dryer or your car or a heater. There's electric heaters, and they can all pretty much be represented as resistors. It turns out, I don't know if physics 1200, I think you eventually learn capacitors actually don't produce work. They're weird things. They interfere with bringing power to places, or capacitances, but that's a little bit above physics 1200. All right, now of course I forgot to change the bottom here. All right, just yell at me if you want me to go back. So, well, I forget exactly, where did I say this? Right. Remember, we need a continuous pathway. And when I say we go from like the whatever voltage here, this is sometimes a negative end or the 0 volts. And current flows from plus to minus. What else? Oh, yeah, you need delta V not equal to 0 if you want I not equal to 0. And you need I not equal to 0 if you want something useful. So delta V, say if this is 5 volts, and remember, wires have no voltage change. So if it's only one resistor, this would be 5 volts and this would be 0. It's not strictly speaking true. Wires have a little bit of resistance. But the point is I want current to flow in my resistor because I want are just, they get used in circuits, but in the everyday world that we deal with, we don't really, a resistor isn't doing anything useful for me. But let's say it's a motor or a heater, unless we have a complete path like this. And the point of it is that we need to create, it's all about creating a non-zero delta V. You should really always think about that. What's the delta V? And because that's what helps you to understand why in the movies, when the bad guy is standing in a puddle and the good guy has the light bulb, lit light bulb, and they throw it into the puddle and kill the bad guy, that's bullshit. It can't happen. Just quickly, I'll say why. Let's say we have the water, bad guy is standing in the water. If the light bulb has the two wires coming in, and it has its base, and it has these two guys here, and it has the filament, right? So you toss it in the water, and first of all, nothing is going to happen if this little filament doesn't break. If it does break, the electricity is just going to go between these two wires. It's not going to go into the water. It's not a liquid. If at most, if this is 110 volts, the water would go to 110 volts and the bad guy would go to 110 volts. But because there's no zero available, nothing happens to the person. So no current flows. And that's sort of represented in this picture right here. If I don't have a complete circuit, both ends, in this example, both ends of the resistor are at 5 volts. Another example is when you see birds on the wires. I mean, they land on those big towers and land on those wires. Those wires are at 100,000, 500,000 volts. And the bird is fine because the bird comes and lands. Let's see if I can make a reasonable drawing of a bird. And so if this is 500,000 volts, the bird is also at 500,000 volts. But there's no zero around unless the bird gets too close to the tower. In fact, when I was young, very young kid, so I was in New York, and instead of the Hoover Dam, we had Niagara Falls. And some bird made a nest, and this bird, poor couple, they built this really great nest, and they eventually built the nest from the wire they were on over to the next wire. And as soon as they touched the other wire, of course, now there was a potential difference, and they got cooked. But it was one of these wires with this huge amount of voltage that the amount of energy transferred melted everything. But this is why birds can land on wires. You need a delta V.
Professor?
Okay.
Professor?
So, yeah, question.
Would the same apply to it?
Yeah, what's up?
Hello? Would the same apply to if a cut electrical cord fell into a puddle? Like
yes. The only one exception. Yeah, I could think of an exception to what I just said. Now, first of all, and that's a great question, Alexander, because and let's go through this because this is pragmatic, right? They basically tell you not to touch these things, and there's a good reason for it, even though you might think you're insulated. Now, when I was a kid, I remember, you know what? I was in high school, wasn't I? So the electric company comes to my high school and they set up this stuff on the stage. And at some point, the guy is up on the stage and says, okay, let's say one of those wires on the top of the telephone pole, you got to keep an eye on the time. So you have a telephone pole and you notice that there's sometimes these are cross trees, but you'll notice there's generally 3 wires up here. And each one of those wires is at 5,000 volts. And then just FYI, you'll see these cans once in a while. And one of these wires will go down to the can. And then those 3 wires come out of the can, and those 3 go to your house. And this is a transformer. And the transformer brings in 110, 110, and a 0. So you have, in case you need 240 or 220 for your dryer or something like that. So you get 3 wires to come into your house. So those wires aren't super dangerous. But one of these 5,000 volt wires falls on the ground. And let's say it's across your driveway and you want to go to work. And they said, okay, what would you do if you needed to move that wire? And so, we all yell, yeah, I'll go get a broom handle, right? So then he pulls the curtain back some more, and there's this booth thing, and it's like a window in it, and you see a crash test dummy inside of it, and the crash test dummy is holding a broom handle, and I think this had bars on it, if I recall. And they had some stylized like 5,000 volt wire with a big sign on it, right? So the guy pushes a button, and this thing, he's holding up like a kabuki sword or a samurai sword, and he twists sideways and touches the wire. And unbelievably, the broom handle freaking exploded. Now, I would guess that they rigged it a little bit, that, if you were wearing rubber shoes and such, But the point is that when you get, okay, you got, it's a good question. So you've heard of insulators and conductors, huh?
Yes.
Right? There's no, there's no wall between the two of them. There's actually just like a fuzzy bit between them. An insulator is just something that has a few mobile, or let's put the conductors have many mobile charge carriers. And in physics, we say they're positive, but of course, we know they're electrons. And a conductor does not, I mean, an insulator does not. It doesn't mean that it does not have that many, doesn't mean it has zero. So the point is that if you get, even if R is super big, if you get V big enough, you're going to get a current. And that's why you'll see in your house, you'll see plastic plugs, plastic outlets. But if you go to see a power station or on the poles, they use ceramics as they have a much higher resistance. So even with rubber feet and such, it still could be dangerous. Now, and that would be like if I'm in some water, if I'm in a substantial amount of water, and the worst would be if I were to hold on to a wire outside the water, because most likely the water is going to provide a ground path. And the voltage into your house, this zero wire that goes into your house, that's also, if this is the earth, that zero wire is also connected to a rod into the ground. So that's why it can be dangerous to be in water because especially like on the floor, it may have a path to ground. But if the electricity, so the safest thing to do, let's say you are dealing with wires and you happen to be near water. If it does drop in the water, the safest thing to do is actually leave it in the water. Don't try to pull it out. And that's number one. Because if you have a wire out here, it's going to travel into the water. So now there's a potential difference. If the wire is in the water, then for the most part, it's going to be 110 everywhere. And maybe there's like zero down here, but then the current is going to be all spread out and it's not really going to pass through you. And the point, if you always remember though, you need delta V not to be zero to get a current. That's how you can stay safe. And you just, when it comes to that 5,000 volt wire, he showed us this electricity guy. They use these really special, heavily insulated special rubber rods, and they wear special boots and gloves. So there's chances to get in trouble there, right? I mean, but the bottom line, like 110 volt light bulb thrown in a puddle. I remember once I was working on my fish tank and the light fell in, and the woman I was dating at the time, like I reached right in to pull it back out, and she freaked, and then I said, this can't hurt me, which is ironic because most physicists don't even get this, right? I learned all this from being a contractor. Okay, so we are digressing a bit. I think what I'm going to do, I'm going to hold off on this voltmeter stuff, and we'll talk about it some more next time. And because, in fact, I think it makes more sense if we do some work on this first. So we'll skip over the meter stuff for the time being, and let's go back to our old friend. This is something you already have, if you look carefully, right? The basic rules of circuits. So we saw this with the capacitors. So you need at least one path. That's what we just been talking about. And all the current leaving has to come back. And any of the sum of the voltage drops, or all whatever happens in the circuit, the voltage drop across the whole circuit has to equal the voltage drop of the battery, right? Or the power supply. This is old hat. Hopefully you remember all this. So the next thing, we went into capacitors, but now this week we're doing resistors. Oh, this is still familiar, right? This is the same basic basic circuit theory diagram. One current path, the current is same everywhere. So that means if I sum the voltage drops of each of the circuit elements, it should equal the battery. So you might make a note in your logbook, instead of spending time drawing all this, refer to, we're using the basic circuit theory here, or the idea, I guess, too, would be, let's go here, draw this circuit, and then put a note to yourself, refer back to page so-and-so for the basic circuit rules here. So this is now for resistors. If you want me to go back, let me know. So just like with capacitors, where we always kept using this equation over and over again, now we're going to use Ohm's law over and over again. And we're going to use this form of it also. So one thing here, this one I put in the dashed box. This is true for any circuit, whether it's series or parallel. If I can calculate the R total and I know the voltage of the battery, I can get I total. Or if I know any one of those any two of those three, I can calculate the other one. And that's always true. Excuse me. Okay. So we go back to our series circuit rule. Well, first of all, I total is the same everywhere. And that's important. You'll see in a minute. And then we go back to rule number 3, that the sum of the voltage drops of the circuit elements have to equal the power supply. So delta V of R1, delta V of R2, plus delta V of R2, plus delta V of R3 has to equal voltage of the battery. So then we can use this form of the equation up here, V equals IR, and good practice says you're supposed to put I1, I2, I3, and I total. And at first glance, this doesn't help us very much. But then we remember that the circuit has I total everywhere. So that means that we could change these all to I total, although that becomes tedious to write this over and over again, but we should hammer it in. But it allows us, because now it's the same I, we can pull out the common term. And then we can multiply both sides by 1 over I. So we multiply both sides by 1 over I, and we're left with this expression for the combined resistance in series. So this is one of the rules of combination that we're going to verify. And we also want to verify, and if you remember the main pre-lab, you're verifying that the current is the same everywhere. And I'm sorry, it's three things we can verify. We can verify the voltage sum rule. We can verify the I being the same everywhere, and we can verify the total R there. So we can verify the I the same everywhere. And two, we can verify rule 3 of series circuits. Which actually, this is rule 2. Rule 2, series circuit. And we can also verify the series rule of combination. Series rule of combination for resistors. Of course, remember, you may recall that it's different for capacitors. So I thought I'd write it down. In the past, I've sort of said the words, but I'll write it down. You should get, when I tell you things like we're going to verify, you should, your red flag should go up and go, oh, I better write this down because Dr. H is going to look for this in my logbook. I'm trying real hard. I want to quantify and write down expectations.
Professor, what was number 3?
Oh, so yeah, Ita, you're always making sure, huh? So we're going to verify the series rule of combination for resistors. Let's make it better. The series rule of combination for resistors. Better? And look at that, just 2 more slides. Okay, so just yell at me if you want me to go back. So this is the parallel circuit from the basic circuit theory. So first thing you observe is there's multiple current paths. Rule 2, analogous to the rule 2 of series. In this case, though, everybody has the same delta V. And the currents in each of the circuit elements have to equal I total. And also, again, I total equals V of the battery divided by R total. That's always true. And, well, give me a minute. This is only for resistor circuits. It's the wrong place for this, but I was jumping the gun. I can see it on the next slide. Oops. All right. So here is the resistor circuit. And that is something I can demonstrate, I guess. Here, let's see. I have to, while you guys are writing this, I'll try and get the things turn back on here. Here we go. And why my wireless headset cut out. I was charging it. All right. So, oh yeah, we have to go over this. So, as I said a moment ago in the wrong place, I total is always equal to V total over R total. It's always true. So you notice, and again, like I said earlier, we're going to use this over and over again, analogous to when we use this when capacitors. So the delta V across each one of them is the same. But in this case, we have to sum the three currents to get I total. So then we substitute in for each of these expressions for I, this guy here, but of course now it's V total over R1, V total over R2, V total over R3. And just to remind you, without having any other knowledge, you would be constrained to put in delta V1, delta V2, delta V3. But because of rule number 3 of parallel circuits, we don't have to do that. We can make them all the same V. So once again, we can pull out the common term. And once again, we multiply by 1 over V total this time instead of 1 over I total. And we're left with the parallel combination rule. So what we can do here, we can verify that, let's see, if it's the rule number 2, so we can verify that I total equals I1 plus I2 plus I3. We can verify that V total equals V1 equals V2 equals V3. And of course, we can verify the rule of combination. Rule of